my name is Thompson, and I've been working in the MRI core facilities this summer, down on the first floor of the imaging suite, under Dr. Carmonic. I'll be talking today about processing and analysis of fMRI data using AFNI software. So a little bit of just basic background in case anyone's unfamiliar with fMRI. fMRI stands for Functional Magnetic Resonance Imaging. It measures brain activity, which is based on generally blood oxygen levels. So it's supposed to correlate a particular stimulus or phenomena, either sensory or motor usually, and it correlates that with blood oxygen levels. AFNI is a set of software programs which are used to process and analyze MRI data, and that's the main software that we've been using this summer. There are a couple of other options, but this is one of the best known. Access to AFNI is used, you're interacting with the command line. If you're familiar with any computer programming, you'll know what the command line is. But so instead of using a graphical user interface, most of the operations are performed at the command line. AFNI just stands for Analysis of Functional Neuroimages. So an overview of a typical fMRI study, or the processing of an fMRI study. You begin with single subject analyses, just to take each subject through the same procedures. The general idea is to align all of the data both in time and space so that it can be analyzed statistically. And then once all the individual subjects have been analyzed, they are put through further statistical tests as a group. So the first part of that, single subject, the input to AFNI consists of three types. The first is fMRI data, which is basically a measure of the functional, the correlations, the activity in the brain across the full brain over time. So that data consists of both 3D and time. The second type of input to AFNI is an anatomical scan, so that you can actually know where in the brain, where in that subject's brain, the activity was located. The third type is a stimulus timing file, so that you know when in your time run a particular event was occurring. So while the patient is in the scanner, you may be giving them cues, either visual or otherwise, for a particular stimulus. So pre-processing at the single subject level consists of a number of different things: motion correction, transform, blur, mask, normalize. These basically are, like I mentioned, in order to align the data in time and space so that it can be analyzed correctly, and minimizing error. The Talirac transform, for example, takes the patient's anatomy and transforms it into a standardized anatomy, which is documented, and so you can have a better understanding of where in the brain you are, where you're looking at. Then the major step in analysis is actually linear regression. The goal here is to determine the correlation between brain activity and a stimuli of interest per voxel. So for each middle pixel in the brain, you want to determine how well that correlates with a given stimulus. So the input to linear regression is the output of all the pre-processing steps that we just looked at. So it's the activity at a particular location in the brain, and the other input is the stimulus time series. So the output of linear regression, and generally what we look at the single subject limit, is a correlation coefficient. Basically, it tells you how well there was a correlation between activity and the stimulus. So this is an example at one voxel located in the anterior temporal lobe. The red represents ideally what the blood flow in the brain at that location would look like. The black is the actual activity, so there's a fairly good correlation here. And that was actually voice, and this is the same voxel looking at a different type of stimulus, which is more covert or thinking about. It's it actually represents a different stimulus. So we can tell this one does not correlate nearly as well as the vocal stimulation. And then for group analysis, like I mentioned, is a series of statistical tests to tell whether or not there is significant activation. And you can do either paired or single sample t-tests. So the overall significance of processing is to avoid false positives, and there have been studies to demonstrate that in this type of study, fMRI, there are significant possibilities for false positives, such as brain activation in a dead fish, which is not a good sign. Some major points to look at are motion correction, timing alignment, and how you're doing the regression analysis. So in conclusion, minor differences in processing can have major differences in results. And I'd like to thank my mentors, Drs. Karmanik and Anderson, as well as my colleague, Aziz Al-Katan. Thank you all very much.